Okay, so hi everyone, I'm Sanjana, and today I'll be doing some combi problems which all have the common theme of having some sort of grid in them. So we're hoping to see different ideas which are applicable in these problems because of the common theme. So this is the first problem. So you can try it, and as you can see, it has two different parts, and it might be better to maybe at least try the first part of the second half. Maybe that gives like a better idea of how to go about the construction. But you can try whichever you feel like trying, and let me know if you get any progress.
Which one did you advise try first?
The first sentence of the second part. So, um, hold on.
Okay, fine, yes.
Yeah, this part. Okay, so I'll give a small hint. So, one common idea that's used a lot when you're trying to bound the number of different types of tiles is some sort of coloring which may give some like size issue or parity issue. So, try to think about the two types of tiles and what kind of coloring might be useful when you're looking at one of them, but be sort of neutral to the other one.
So for the first one, we can maybe do some three coloring based on like x plus y, and
Um,
then for the first one, it would cover one of each color,
wait,
and the
which part are you talking about?
no, like for the second part only, like
Okay,
a coloring which for which tiles of type A only cover equal numbers of all the colors.
okay, that's a good idea. So you're saying that, like, do you have like an example of the coloring or just
Yes,
an?
yeah. So like you label it from the top up to
Mhm.
down and left to right, and based on x on the value
Like
of x
this?
plus y mod 3.
X plus y mod 3.
Yes.
Okay, so it's like a two coloring that you're suggesting.
No, 3 coloring mod 3.
Oh, okay, mod 3. So this, say, 2 mod 3. So it's something like this.
Mm.
Okay. So let's see here if we have a tile of this type. It's what was the like the argument that you had? Like if you have
Oh
a
wait,
tile of,
we are allowed to rotate it. Sorry, I didn't
yeah, we are
consider.
allowed to rotate.
Yeah, sorry, it doesn't work there.
Okay. Okay, so even if that approach didn't work, what was like basically going on was she was trying to make the number of tiles covered by the A type equal. So if you had something of this form, that would have one of 0, one of 1, and one of 2. So that would work for the A type tile. But what we're trying to do is we're trying to minimize the tiles of type A. So we want some sort of constraint on that. So maybe it would make sense to make everything equal for type B in the same way so that you get some sort of constraint on type A. So maybe try something similar but for the second type of tile.
I guess if we label it so that each one, there are four colors and it goes 0, 1, 0, 1 and one row, and then 2, 3, 2, 3 in another row. And then it goes back to 0, 1, 0, 1. Then each square will have one of each. And
Yeah,
then there will be more of some colors than others. So then the difference will have to be used. Will have to be diluted tiles of type A.
yeah. So what he's doing is he's basically dissecting the grid into like 2 by 2 squares, and in each one he's coloring 0, 1, 2, 3 in this pattern. And the logic behind this is if you have a B-type tile, it's always going to cover four different like numbers, like 0, 1, 2, 3. But the thing is you have here you want like 1011 by 1011, or in general it's like an odd number. So it's like 2n plus 1 by 2n plus 1. So you're not going to have an equal number of all the tiles, and that difference which you're getting, that should be made by the A-type tiles. So let's say you have a 2n plus 1 by 2n plus grid. So up till here, there's going to be 2n here and 2n here. And in this last column, you're going to have only zeros and twos. Here you'll have only zeros and ones. And in this one, you'll just have a 0. So now we can sort of like quantify the things that we have. So we know the number of squares of each type. So if we want the number of zeros, we can calculate it. It's 2n squared, so 2n times 2n, plus over here we'll have another n here and 1 here. So the total number of zeros would be, this is divided by 4. Yeah. The total number of zeros would be n squared plus 2n plus 1. I hope that's clear to everyone, because in this one you have 4n squared squares in total, but 1/4 of them are zeros in this area. And then the others you can just calculate it. And the number of ones is going to be similarly n squared, but then you're only adding 2n from here and here. And the
Shouldn't it
number
just be
of,
n because the right column doesn't have any ones, only the
oh
bottom
yes, it's,
bottom
yeah,
row.
n squared plus n, sorry. Yeah. And similarly, the number of twos is also going to be the same. And the number of threes is going to be just n squared because it does not appear in the, like, outside of the main square. So we know that, so can we like relate this to the number of tiles of type A and the number of tiles of type B? So for a tile of type A, we know that it's like leaving out some square here. And this can be a 0 or a 1 or a 2 or a 3. So based on that, we can classify the tiles of type A into 4 different types, right? The ones that leave out 0, let's call it A0, and the ones that leave out 1 and 2 and 3. We also know there's like some number of type B. So we have these two quantities, like these two sets of quantities. So can we form any relations between them that leads to some bound on the A's? So you can try to do that for some time.
Have to be,
Sorry?
yes, sorry, there have to be at most n squared squares. But then if we look at it in this case, that will become 2021 squares left. 21 small squares left, and 21 isn't divisible by 3. So there has to be fewer squares than this, in fact.
Okay, how
And
are
then,
you getting the initial numbers?
because if there have to be at most n squared square since each square occupies exactly one which has number 3 and there are n square of them and they can't overlap. So then
Mm,
in this specific case there are 21 left,
okay, yeah.
but then there has to be one square missing because otherwise we can't directly tile it with
Okay.
dominoes. So at least 2025 squares have to be tiled by the tiles of type A.
Mm, okay. Yeah, that's actually very close. So I think what you're trying to do is you're saying that suppose we minimize the number of A tiles which contribute to 3. So you're saying we'll have at least n square B tiles. So yeah, what we are trying to do is like very similar to what you said. So if we just try to write this in the form of some equations to like have as much of formality as possible. So let's see what all contributes to, for example, the tiles which into the 3 squares. So each B tile is going to have a 3 square, but also each A0 and A1 and A2, because none of them leave out a 3 square, right? And similarly, we can write the exact same type of equations for all the others. So this is going to be B plus A1 plus A2 plus A3, because none of these leave out 0. And similarly for these two. And in fact, since both of these are the same, you can see that A2 and A1 must be equal. So that's one relation you get. So maybe we can get more sorts of inequalities from these equations. So try to see if you can figure that out. It's very similar to what Vera was saying, I think just a little bit stronger. So I hope it's clear how we get these equations. Like we just look at all of the tiles which are going to give us one of each of these three and these four numbers. And we're just adding them up and equating it to the total number of numbers we know is going to be there. So now our goal is to minimize the AIs. So just try to see what happens when you try to make that number as low as possible.
We need to maximize the sum of AI, right?
No, we need to minimize the sum of AIs. We want the minimum possible number of um, tiles with like this type tiles. So we need to make it as low as possible. Okay, so if you notice, then like if you take the difference between, say, the 2 tiles and the 3 tiles, that is the difference between this is A1, I think. Yeah. So that's the difference between A3 and A2. So like the difference between each of these is the difference between two of the A's. So maybe from that you can like figure out which one is supposed to be the smallest and how you can minimize the rest of them if you say take the smallest one to be 0, for example. So here you're getting that A3 minus A2 is equal to n. What else can you get? Okay, so similarly, we also get from the first one, we get A3 minus, from these two, we get A3 minus A0 is equal to 2n plus 1. And you know, A2 is equal to A1, so they're the same. So now it seems like A0 needs to be the smallest one, right? So what we can do is we can just say A0 is some x, and we want this to be as small as possible, so preferably 0. Then A3 would be x plus 2n plus 1, and A2 would be x plus n plus 1, and so would A1, just from these equations. It's like B sort of cancels out from all of these. So if you get one of the other AI, you can sort of solve for the others. So we're just solving for the others here. And when you add them up, the final answer must be of the form 4x plus 4n plus 1. But this x is sort of arbitrary, as in this is the thing you want to minimize, and this is 3, sorry. Yeah. So if you take x as 0, the remaining will still be 4n plus 3. So you know that the number of a's has to be at least this much, even with the minimum x. So in our case with 1011, you know that, so you're taking 1011 as 2n plus 1. So n becomes 5005. So 4n plus 3 is 2023. But yeah, that's your bound. So in general, for 2n plus 1 by 2n plus 1, you're getting a bound of 4n plus 3. And now we need to find a construction which exactly achieves the bound. And that is sort of like the point of the first part. So the first part is asking you for the construction for 7 by 7. So specifically when n is equal to 3. So maybe try to find a construction for 7 by 7, and then we can try to maybe extend it to any larger n, because directly finding a construction for a random n seems sort of like harder than trying to generalize it from a small case. So maybe try this one for some time now. And then we'll see if we can combine them to find the final construction.
It would be 4n plus 3 in this case become 15, which means there's only one tile of type
Yeah,
B.
that is true. So that's a very good observation. 4n plus 3 is 15. So you have 15 tiles of this type, which means 45 squares of like covered by these tiles, which means you have only 4 left because 49 minus 45 is 4. So you have only one tile of this type if you want to achieve this construction. So that's a good starting point. So you can just try putting one tile in somewhere and then filling the rest using the other type. So I'll just use this one for the construction.
Sorry, can you repeat that idea, please?
Was it the bounding part or this like 45 thing?
Yeah, that 45 thing. My
Okay,
net.
okay. So we are trying to find a construction for 7 by 7. So for 7 by 7, we are taking 7 equals 2n plus 1. So n equals 3. So in that case, you're getting 4n plus 3 is equal to 15. So by the bound we were doing, we must have at least 15 tiles of this type. But that means that 45 squares are filled with tiles of this type. So you have only 4 tiles remaining, which means only one tile of this type can be used. Does that make sense?
Yes, thanks.
Yeah, no problem. So yeah, this construction is not anything like very intuitive. You just sort of have to try, like do trial and error for a while until you find it. So if anyone gets a construction, then you can say it. I'm talking about the specific one for 7 by 7. So I'll just give a small hint because this is not really the main part of the problem, but we can start off with the single B-type square here and now just try to fill the rest in some way.
Yeah, I feel like I got it.
Okay, could you describe it? Like we can number the tiles.
Uh, yes, I think we can fill the 4 by 4. Let's see. We can fill the 6 by 6 thing completely, but with the only the trominos, but only
Mhm.
one square will be left, and we can
Okay.
then do all the even squares where one square will be left, and I think we can fill the other dominoes in the empty spaces.
Wait, so by 6 do you mean like this one or like which 6
No,
by
no,
6?
no. Oh no, I think I messed up. Sorry.
Okay, it's okay, no problem.
I think I got the construction, but I'm not sure how to explain it.
Okay,
It's
like
not
this.
intuitive.
Yeah, this part is not very intuitive. Can you like tell me just where to place the dominoes and I can try to do that?
One above the square, like a half T,
Like this?
yeah,
Okay,
and then one next to it.
like
Oh no
this?
no no, yeah, and then
Okay.
down below that another half T.
Oh,
No, the other way, half T, yeah,
okay.
and then another L beside that,
Mm-hmm.
and then an ulta L, like
This?
yeah,
Okay.
and then 5, 6, and then 2 and 5, one above it. So you make a
Like this?
rectangle,
Okay.
and then another one above it,
Which orientation?
the same orientation above it, and then the
Okay.
same orientation above it,
Okay.
and then keep making L's till you complete that rectangle.
Um, okay, but then you have a problem here. So do
So
you want
we
to make
can,
an L here?
yeah,
Okay.
and then go to the corner,
Yeah,
and
and
then make
now
an,
you can make rectangles again,
yeah.
right? Okay. Yeah, this is actually nicer than the one I had. So she just made a lot of rectangles, which are a nice thing to do in this kind of configuration. And then there was just one L left and you fill that. So yeah, this is nice. And yeah, this is your construction for 7 by 7. So now we want to try to extend this to a general 2n plus 1 by 2n plus 1. So when you're going, so right now we've used exactly 4n plus 3. So now we want to essentially go from 4n plus 3 to 4 times n plus 1 by n plus 1 time plus 3. So you're increasing this one by 4. So you want to somehow extend this and increase the number of rows and columns by 2 and use exactly 4 of these while extending it. Because if you can do that in general, then you have a general construction for n greater equal 3. So you basically just need to fill these rows mostly using the other type. So mostly using type B, but using 4 of type A. So if someone can come up with a construction for that, we would be
Use
done
the
with the
same
problem.
rectangle idea, I think.
Okay, but we can only use 4 of type A.
So we can have two rectangles, right?
We can, yeah.
So we could put like both the rectangles on the edges of the column and the row.
Then it's an
You,
even number.
wait, do you mean like this?
No, no, like on the other side, other end.
Ah, okay. Yes.
And I mean, I could be making a mistake also. So you do that, and then we
Mhm.
just fill fours unless I'm making a mistake.
Mm,
We just fill the 4 blocks.
right. You just need to make sure this does not have parity issues.
Oh yeah, we just need to check that.
Yeah, so here this is becoming like a multiple of 4 plus 2, which means, and this is equal to, no, this is becoming, yeah, this just has to be an odd number, right? Because we're using 2, 2, and then 3. So yes, as long as this is an odd number, which you know is true because it's always 2n plus 1, yeah, this is going to work. Basically, you just start with this corner here, you start with square, and then you push it till the end until you have like 3 left, and then you make a rectangle. That's always going to work because n is odd. So yeah, this works. So you can just keep on extending it in this way and keep on going up and to the side. And this is always going to work for 2n plus 1 by 2n plus 1 square grid. So I hope this was clear to everyone. I'll just go over the whole thing once more. So what we started with was we wanted to develop a coloring to sort of distinguish between A and B and to get a bound on A. So in order to get a bound on A, you sort of want things to be neutral or equal for B, which is why we did this type of coloring over here. And this lets you like very specifically characterize the A tiles because each A tile is leaving out exactly one of these. So now you have a way to relate the number of A tiles and the number of tiles in the grid. And that is what we did with these equations. And we manipulated them and we got the minimum possible number of A tiles, which is over here. And using this, we were able to form a construction for 7 by 7. And then we were able to extend that to a general case. So that was the main idea of this problem. So if anyone has any questions, you can feel free to ask now. Or else
I
we'll
think
move
the
on to.
most counterintuitive part was like we have to have more of uh we have to have less of B than A. And if we were to start like making constructions, we would have gotten stuck. Like I got stuck the first time I saw a related problem. So how should I have like gone for that?
I think so. Yeah, in this case, it's very likely that if you try part 1 first, you might just get stuck. But now you can see that in part B, you're being asked to find a bound. So maybe the bound is going to help you with the construction. So that can motivate you to try the second part first. So yeah, that could be
Yeah.
something you can do.
Why do we started with 7 by 7 to just ensure that 4n plus 3 does not exceed the total number of tiles, right?
Yeah, exactly. Like if
That's
it's
it.
less than 7, then it's not going to work. So yeah, and in general, with problems with 2 parts, like especially if it's on a contest, it could happen that maybe one part is going to um, motivate the other part, or one part might help you solve the other part. So you can switch between the parts that you're trying. And yeah, starting the induction from the 7 by 7 case, well, like you're given, like that's one of the parts of the problem, right? So they're probably sort of trying to give you a hint. Like they're not just going to put that there for no reason. So maybe if you find a construction for the 7 by 7 case, that could help you solve part 2. So yeah, that's the main idea. Okay, so let's move on to the next problem. So you're given, so in this one, you're already given a coloring, you're given a chessboard coloring. And what one person does is, so you have 2 players basically, and the first person swaps rows and columns in some order, and the second person wants to restore the coloring. And what's the largest number of swaps the second person is going to need? So this is a slightly harder problem, and I would suggest that maybe instead of directly trying to find the answer, you could try playing around with this first and maybe make some nice observations. And if you have any ideas at all, feel free to speak up.
I have a genuine question. Like on contests, how do we do like grid problems if we don't have graph paper?
Well, what you can do is you can use a pen to draw a grid like with a scale, and then you can use a pencil to work in it. So you can easily erase
Doesn't
everything.
that take a lot of time?
It does take some time, but it's either that or you'll have to like manage without the grid. So
Yeah.
your choice. Yeah.
Wait, so what if you just swap, like in our case, like in
Mhm.
our chessboard, what if you just like swap the blacks with the whites? Does it still count as a chessboard coloring?
It does, but like you can assume you're starting with more like with blacks on the corners.
Yes. So if Isaac or whatever, he swaps and he makes it such that there are only whites on the corners,
He
but it's
can't
still
do that,
chessboard.
right? Like if n is odd, then he can't do that because you can't change the number of squares, right? Like by swapping a column and a row, you're just changing the order of them, right? So
Okay, yeah,
in
changing
the
the order, fine. Okay.
yeah,
Got
he's
it.
not changing the colors. Yeah.
But like, what if in a 2 by 2,
Okay.
we have a chessboard and then he just swaps like the two rows, whatever, or columns. It
Yeah.
just, does it still remain a chessboard? Do you still count that as a chessboard?
It, that's just the board you get, and what the second person wants to do is he wants to restore it to the original state.
So that
So,
would mean, because when you swap it, like, let's say black was on the top left corner and you
uh-huh.
swap the, fine.
Okay. So what do you
And
want to
then
do?
you swap the two, fine, yes. So does that still
Yeah.
count as
Yeah,
the,
you want to get it to the original. So if you started with this, you want to get to this itself.
okay, then.
Okay.
Do the rows and columns have to be adjacent?
No,
Or
no, he can
can,
swap any two.
yeah, thanks.
Sure. Okay, so I'll give a small hint which might help you maybe simplify the problem. So if he's swapping some two columns and he's swapping some two rows, um, look at what happens to the board and think about if the order really matters. Like, does the order of a column swap and a row swap change anything? And if so, what does it change? Like, suppose in one case he's first swapping the columns and then swapping the rows. And suppose in the other case he's swapping the rows first and then the columns. So does this have any difference?
Like the four intersection squares don't change.
Those don't change. And what about the other squares? Do
Don't
And
they
the
they?
other
change?
squares have to be opposite.
Um, why is that? So if I'm swapping, okay, let's just copy this.
With the other squares, just swap, right?
Exactly.
Yeah, exactly. Like they just swap. So there is no change if you change the ordering. Because each of these, like this one either goes here and then goes here, or it goes here and then goes here if you swap the rows first. And similarly, all the, like these four squares, all of them go to their original positions in both cases. And for the other squares, it's kind of easy to see that it doesn't matter if you swap the row first or if you swap the column first.
We
So
could
that
just swap all the rows in one go and all the columns
exactly,
in one go.
exactly. So that's like an observation that simplifies the problem significantly. So we know that it's assumed that all row swaps take place and then all column swaps take place. So you can also assume that Elijah's row swaps, which he's going to make after Isaac, you can imagine that they happen before Isaac's column swaps. Because, like, you can imagine he can just see into the future and then do his swaps before Isaac makes his column swaps. And that just means that all the row swaps are going to take place and then all the column swaps are going to take place by both the people. So now it kind of, but not exactly, suffices to look at the rows and columns separately. But there's also some things you still need to be careful about. So yeah, you can try it this way now.
Like even with that, you would have to be careful about the intersections, right?
Well, the intersections don't get affected no matter whether you swap the rows first or columns first. But like the thing is, if you're working with an even grid, then something that is of this form, it could end up being in this form somewhere else, right? And that might still be okay. But if you're working with odd, then something that starts out like this will need to end up like this itself. So that's why you need to be a little bit careful about how you want to return back to the original state. But
Yeah.
yeah, you can safely assume this. So yeah, if anyone has any confusion about how we are doing this, then you can ask in case it wasn't clear.
At least ceiling of n by 2 would be required. Unless it's 1, because every single every single point you have you have to change the case you have to change most of the points, then that will require you to swap enough of them to
Right.
cover all the points you want to change.
Okay, that sort of idea seems correct to me, but you also have to kind of look at even and odd separately. So you're saying n by 2, are you saying that for the general case?
Yes, I think floor of n by 2 at least.
Okay, that is true, but I think for the odd case, it's going to be even more than that. So let's look at the odd case first because it's simpler. So if you're doing the odd case, you know that each column and each row must return to its original case. So you know that first all the row swaps are going to happen. So the columns are just going to remain fixed. So it just suffices to look at one column. Without loss of generality, suppose it just starts sentence with black. So some swaps are going to happen and you want to be able to restore it to its original state. Because after the row swaps, you're going to do the column swaps, but the column swaps don't affect the column itself. So the columns all have to be fixed before the column swaps happen. So when Isaac does his row swaps, then Elijah will do his row swaps, and these must fix the rows. So given that Isaac has messed up this columns orientation, what's the minimum number you need to get it back to this original state? Can we figure that out? Okay, someone's asking if it would work to consider the extremal case. And okay, so what we are trying to do is essentially that, like we're trying to find a bound and then that will automatically be your extremal case in a
I think
sense.
if you have 2k plus 1, I think it's k.
Okay, that is true. So if
So,
n is 2k plus 1, yeah.
so because we know that one black will remain in its position for sure,
Yes, that is
like
true.
in one of its whatever. So like
Mhm.
the worst, if you would like to say, would be like all the blacks are in the whites and
Uh-huh.
all the rest of the whites are in the rest of the open blacks. So if you just
Yes,
like swap them, you
that
will
is true. Yeah,
work it out.
so like we're just supposing that let m blacks be in the wrong position, then m whites would also be in the wrong position. So then you can just do m swaps. And the maximum value of m would be k because you can't have more than 2k in the wrong position. And yeah, yeah, go on.
I think it might actually need more than that in some cases. It might even take more because if we look at tree, then
Okay.
in that case we can actually have something which requires two.
Mm, okay, can you give an example?
So there's a 2 by 2 square of black squares, and then next to it is two almost of white squares, and then other than that there's also one black square.
Okay, so you're talking about the 3 by 3 the whole grid. Yeah, this is just for the rows part. So after this, we'll have to do the same thing for the columns. So it's gonna be double of this.
Oh yes.
Yeah. So yeah, you need at most k to fix the rows. And then, so this is for the rows. And after this, the column swaps happen. So by the same logic, you'll again need at most k here. So in total, you'll need at most 2k, which is at most n minus 1. This is for odd. And for construction, it's just like the same thing, like it's the extremal case. So what Isaac can do is he can swap, like if you have a column and this is labeled 1, 2, and so on till 2k plus 1, he can just swap 2 comma 3, then 4 comma 5, and so on. And this will force Elijah to have to reverse all of these swaps because you need to get because this will have exactly this equality case when m is equal to k. So the bound is exactly the equality case that we are getting. And so that will just force those many swaps. And same thing happens in the column case as well. So this is for odd. Now for even, the issue is that if you are given like a column and it's starting with black and it's ending with white, you don't know that it has to go back to its original one. It could go back to the same thing, but it could also go back to the opposite one, right? And same thing happens for the second part. So if you have a row and it's starting like this, then it can either go back to the original one or it can go back to the opposite one. So if this happens for all the for all the columns in the first part, then this needs to happen in the second part, because this means that you're going back to the original grid. So when the column swaps happen as well, again you should be going back to the original grid. In the second case, you're flipping the grid because everything is going to its opposite. So then you'll need to flip it again. So there's like two choices you can make basically. The first choice is you do this one and then this one. And the second choice is you do this one and then this one. And since you're assuming that Elijah can just see into the future and know I6 moves, he can choose which one to make. So now we need to find the minimum number of moves he can make. So for example, if the green option takes more moves, he's just going to do the blue one. So first of all, can we like figure out how many moves it's going to take in each one? And then we can figure out how to get the minimum. So the idea of looking at the wrong paths again, that is going to come in useful. So maybe I try to use that. And by wrong paths, I mean that suppose you want the black squares to go to evens and you want the whites to go to odds. We're looking at the number of blacks which go to odds and whites which go to evens. And those are going to be the same because otherwise, if you do some swaps, you'll just get that there's too many odd squares. And that's a contradiction. So I hope this argument is clear. And if there's any confusion related to this, then you can ask because this part can be slightly confusing.
Wait, I don't get it. Why, if you flip the grid like in the first step, like why is it necessary to flip it in the second? Like we could just like arrange the flipped ones into the flipped places and get the original, right?
No, okay. But what happens in the first case is that like after the grid gets flipped, everything is like reversed, right? So if you started with black over here, now it's white here. And now he's only swapping the columns. So you need to get a black column here, right? Instead of a white one. So that just means that the entire thing has to flip again. It's like you have two options. You can go from original to original to original, or you can go from original to flipped to original again. And that's the only option you have because when you're doing the row swaps, all the columns are identical up to flipping because
Yeah.
you can't swap the columns themselves.
Okay.
Yeah. So if you're assuming that all the row swaps happen first, it just suffices to like look at what's happening to one column. Does this make sense? I can explain it again if you want.
I think I'll need another explanation. Sorry.
Okay, sure. So first Isaac is doing some row swaps, right? So suppose you start out with a column that's like this,
Correct.
and we end up with something else, and then Elijah wants to take it back to something. So suppose Elijah takes it back to the flipped version, right? So that means that if this column went to this one, some column that
Other
start,
columns will come back
yeah,
to them.
exactly. So
Okay,
does it,
that way.
yeah, so the entire grid flipped its colors, right?
Correct,
So
yes.
that is going to have to happen again.
Okay, yeah, I got it.
Okay.
Thanks. So like we want to find the case when if there's a position in which even if after we switch the colors, it'll take the same number of moves to come back to the black, white, black, white. You're muted, but okay.
Yeah, sorry. Yeah, I think that is what eventually ends up happening. So, yeah. So again, suppose over here you have, say, X wrong pairs. I hope it's clear what a wrong pair is by now. Like X black in the in the wrong parity and X white in the wrong parity. So over here, if you're going back to the original, you will take X moves. But suppose you want to do the opposite thing, like you want to go to the flipped version, then
N minus X, I guess.
exactly, because yeah, you'll have X wrong pairs means you have two X wrong things. So yeah, it'll be N by 2 minus X actually, right? Yeah, because you have two X wrong things. But then in the opposite case, the wrong things become correct
Oh
and the
yes,
correct ones
yes.
becomes
One
wrong.
flips to, yeah.
So yeah, it becomes N minus 2X and then divided by 2 because the moves is the number of wrong things by 2. So here you'll have X and then minus 2 by X, N by 2 minus X. And over here, suppose it's Y, again, similarly, you'll have N by 2 minus Y. So you can choose either X plus Y. So the first option, the green one, gives you X plus Y, and the other one gives you N minus X plus Y. So the minimum of these is always going to be less than or equal to N by 2 because you're looking at the minimum of two things whose sum is N, right? So from this, you can just construct a case where both of them are equal. So for example, if Isaac just swaps all the rows, for example, then X becomes N by 2, this becomes 0, Y becomes 0 because he's not swapping any columns. So this one becomes N by 2. So then you are achieving an equality case. So that's how you end up with the final answer of N by 2. And that itself is the construction. I'll just explain this last part once more in case it was confusing. So for the even case, again, I'll start from the beginning. We are first swapping some rows. Elijah is going to fix those in some way. Then Isaac swaps some columns and Elijah is going to fix those. So when Isaac swaps the rows, like each column is going to change in some way. So this column is going to go to something. And if Elijah fixes it by sending it back to the original column, that's okay. Then for the rows also, now only like when the columns get swapped, only the individual rows get affected. So he's going to have to send each row back to its original case. So that's the green one, like this one and this one. Now the opposite case is when Elijah is like, okay, maybe if I send it back to the opposite one, it's going to have fewer steps. So after Isaac does some swapping, he sends it to the opposite uh, configuration. But then when he does that, each column gets entirely swapped as we saw here. That means the grid gets fully flipped. So in the row case also, he's going to have to flip everything. So that's the blue option. So he's going to have to choose one of the green one and the blue one, whichever one has fewer moves. And then similar to before, we calculated the number of moves each one is going to take at maximum. And we got this. So the minimum has to be n by 2. And the construction is just straightforward. Like this construction is just swap all row pairs. 1, 2, 3, 4, and so on. And then he only has to like return the columns to their original state, and he doesn't have to do anything in the second part. So I hope that was clear. Yeah, this was a slightly more confusing problem, so I'll wait some time in case anyone has any questions or wants some time to digest. So yeah, feel free to ask if anything is not clear. Okay, so I hope it's fine for everyone. And if any questions come up later on, feel free to ask them. Okay, someone's asking why n by 2 minus y. So again, we're using the same logic here. So suppose you have y wrong pair. So that means you have y black in the wrong place and y white in the wrong place. I hope you understand why these two are equal, because otherwise you'll just get like a size issue. So you have like these two y wrong things, but if you swap a black and a white, both of them are going to become correct. So you just have to do y swaps over here. That's how you get this y. Now how you get the n by 2 minus y is, here you have y black in the wrong place and y white in the wrong place. But in this case, you're aiming to return it to the opposite state. So here if you had y black in the wrong place, now the remaining blacks are going to be in the wrong place. So now you're going to have n by 2 minus y black, which are wrong. And the remaining whites are going to be wrong because you want to return it to the opposite. So n by 2 minus y whites are going to be wrong. So again, you just need to do n by 2 minus y swaps to return all of these to the correct state. So, okay, so I hope that's clear. And yeah, if anyone has any more questions, they can ask. And yeah, now we'll move on to the next problem. So yeah, we'll do one more problem. So this is, you have an n by n grid and each cell has some real number and the rows are pairwise distinct, which means any two rows, they differ in some column at least, like at least one column. And we need to prove that we can remove some columns so that the rows stay pairwise distinct. And this requires like a very specific idea, which is sometimes seen in grid problems, but it's not very common. So you can try this for some time and yeah, I can send the source in 1 second. Yeah. So anyway, this problem you can try for a while and say any ideas that you get, and then I can give the hint that's like the main core of this problem.
we will have an edge between two rows and there is some column which you can
Yeah.
delete and then they're the same and then we get a cycle.
Yes, yes, that is the idea. So, what you're doing is, you know that till you're assuming the contradiction. So you're assuming that whatever column you erase, there will be some rows which become the same. So if I'm removing, say, this column, you're going to be able to find two rows which are now the same. And that means they differed in this column only. So, and that is true for every column. For every column, we can find two rows which satisfy this if you're assuming the contradiction. So we want to somehow condense this information into some sort of structure. So we just like look at each of the rows. So say row 1, row 2, and so on. And if two rows are the same except for a certain column, say CI, then you just connect those two rows and label it with that column. So if you can kind of see the structure that we're working with now, that might help a little more with the problem. And we know that we're going to have one edge for each column. So that gives us n edges in total. And if we are looking at this as a graph, we have n vertices.
A cycle, huh?
Yeah, and n edges. So this always means that there is a cycle. And the proof of this, you can do induction. Yeah. So if you have some vertex that's has degree 1, you can delete it. And then you'll have like n minus 1 vertices and minus 1 edges, and you can use induction. If there is no such vertex, that means every vertex has degree at least 2, which means you can just keep traveling and eventually you'll get back to some vertex you reached before. And you can keep going because every vertex has degree at least 2. So in this case also you have a cycle. So that is the proof of this statement. And it's a useful thing in general, like even in like pure graph theory questions, this kind of thing can come in useful. So it's something to remember. If you have n vertices and n edges in a graph, then there must exist some cycle. So now you have this graph and you have the vertices corresponding to the rows, and you're connecting them with edges corresponding to the columns. And you know that there's a cycle. So let's assume it's from, say, R1 to Rk. Like you can just call them that without loss of generality. And let's call them C1, C2, and so on. Like the labeling does not really make a difference. And okay. So you know that if two vertices are connected by an edge corresponding to a column, they are the same in all the cells except for that column. So what kind of information does this sort of cycle give you? You can try to think about that.
So in column 1, from row 1 is okay, and like if we go along the other route, we'll find out that the component in the first column is same of R1 and R2.
Yes.
But yeah, it's different.
Yeah. So what you're doing is you're just going this way first and like looking at the information you have. So in R1 and R2, you know that they are the same in everything except C1. So they're the same in C2, C3, and so on till CK. You know, R2 and R3 are the same in C1, C3, and so on till CK. So from this, you can get that R1 and R3 are the same in everything from C3 onwards. Right? And now you can do the same thing. Like R3 and R4, you know, they're the same in everything except C3. So that means that R1 and R4 are the same in everything from C4 onwards. And you can induct in this way. So finally, what you get is you get that R1 and RK, they are the same in exactly CK. So that means that, but like here you have this edge as well, right? And that says that they're the same in everything except CK. And that's a contradiction. So yeah, that's how you approach this problem. So the main idea was you first assume contradiction because it seems like a neater way to go about this. And then you see that, okay, each column kind of corresponds to two rows. And you sort of want to form connections in that way. And okay, say these two rows have this column which corresponds to them. If you have some other row and you know something about these two, then maybe you can say something about these as well. And you sort of want to connect things in that way. And that leads you to sort of form this graph, which lets you like directly connect rows based on the column that is relating them. And then it just comes down to using this lemma and just writing down the information you have, which leads to a contradiction. Okay. So I don't think we have time to do another problem. So if anyone has any doubts, you can ask now and then we can wind up the class. Yeah, I hope this problem was clear to everyone. Also, someone had asked for the source of the previous problem, so it's from the British Math Olympiad. I think I can send the paper as well. I can just try to find it. Okay, so if okay, so sources for the other two problems. This problem, I don't know the source, like I've just come across it before. The first one is from India Agmodiosity 2024. And yeah, there were some more problems which I had, which I'll be putting on the PSET. So you can try those as well.
And what is the last problem?
Yeah, this one I don't know the source. I've just seen it before and wanted to use it. So yeah. Yeah, if you have any questions, feel free to ask on Discord as well. So I hope everyone enjoyed the class. Thank you for attending.